In this video, we are going to discuss about the channel coding theorem. On completion of this topic, students will be able to understand the concepts of channel coding theorem. So, why we need the channel coding? See, the challenge in this digital communication system is more cost effective, so that in transmitting the information we need more challenges in transmitting the information from one end to another end, in rate or in level or reliability or quality. So for this thing we need channel coding to overcome these challenges in the digital system. The two key system parameters are transmitted signal power and channel bandwidth. The main thing, the power spectral density of the receiver noise, and these parameters which we are using as the key parameters determines the signal energy per bit to noise spectral density ratio, that is we call it as EB by N naught. And the main thing why we are going for this channel coding is, if a discrete channel has a capacity C and the source generate information at a rate less than C, then there exists a coding technique that the output of the source must be transmitted over the channel with low probability. So here the maximum rate for mapping the incoming data set into channel input sequence should reduces the redundancy to improve the effective of the system. And this channel coding in the communication system, actually why we are introducing means to reduce the redundancy, that it introduces the redundancy with the control, so that the reliability will be or efficiency will be improved. And this source coding will reduces the redundancy to improve the efficiency of the system. So the noise present in the channel creates unwanted errors between the input and the output sequences. So this will be very low, nearly less than or equal to 10 power minus 6 for the reliable communication. Mainly this channel coding consists of two parts, that is one is mapping and another one is inverse mapping. So it is very possible to communicate the discrete data system, that is we call it as digital information, to compute the maximum rate through the channel. This result was finally presented by 1948 by Claude Shannon. So from his name we call it as Shannon's coding theorem. This Shannon's lift or Shannon's capacity of the communication transfers the rate of channel for a particular noise channel. Let's see the channel coding. So let us consider the discrete memoryless channel del with the entropy H. Ts indicates the impulse, channel capacity C, and the channel that we used for every seconds for time period Tc. So here the maximum capacity of the channel is C by Tc. So the data sent is H del by T naught. If this H del by T naught is less than or equal to C by Tc, then it means the transmission is good and it can be reproduced with a small probability of error. In the case of C divided by Tc, that is the critical rate of the channel capacity, this system is said to be the signaling of critical rate. So hence the maximum rate of the transmission is equal to the critical rate of the channel capacity for error free messages which can take place over the discrete memoryless channel. This we call it as channel coding theorem. Here this Shannon's theorem states that in a noisy channel with a capacity C and information rate R, if R is less than C, then there exists the probability of error, and if it is greater than C, there will not be any error. If it is greater than C means this probability of error does not happens, and these codes will be having the probability of error greater than the minimum level, and this level will increases as the rate gets increased. So the information can be guaranteed to be transmitted across the channel beyond the channel capacity, and they does not address the rate situation in which the rate and capacity are equal. This channel capacity can be calculated based on the physical properties, that is Gaussian noise, using the Shannon's Hartley theorem. For every discrete memoryless channel, there is a property that epsilon is greater than 0 and R is less than C. There exists a code length n with a rate R. and this decoding theorem has the maximum block error of less than or equal to epsilon. Thank you.